Now we want to look at the first of two methods that we can use to solve a system of equations algebraically. Solving a system by graphing absolutely works, but it has some drawbacks. One is, again, it depends on how well we draw our lines. Two, if our solution isn't integer values, if we get decimal or fractional values, it can be nearly impossible in some cases to see the exact point of intersection. And sometimes we just don't know how big to draw our graph. All the examples we looked at so far, the points of intersection were between values of -10 and 10. But sometimes the values could be much larger than that, much smaller than that. So there are some drawbacks to graphing. So what we want are some methods that we can use, some algebraic methods that we can use to solve these systems. And what we're going to look at is using a method called substitution, where we will first reduce the system of the 2x2 system to a single equation with a single variable. This process of substitution is designed to rewrite the problem as something simpler that we can solve, and then once we have our first solution, we can use that to find, or once we have a solution to one of our variables, we can use that to find the solution to our second variable. So let's label our two equations again so we can reference these. We have equation 1 and 2, and what we do with solving our systems by substitution is select one value to substitute into, or one expression to substitute into the other. What we're going to do in this first case is use the fact that y equals -5/3 x minus 9, our first equation. We're going to take that expression, which we know is equal to y, and we're going to substitute that into the second equation for y. So we're going to rewrite equation 2 as, instead of y equals, we're going to rewrite it as -5/3 times x minus 9 is equal to -2/3 x minus 6. All we've done is made a substitution. In place of y, we're substituting in this longer expression that we know is equal to y because of that statement we have in the first equation. And now we have a single equation with one variable, and we can solve that using methods we've established in previous sections. The first thing we can do is just drop those parentheses. We don't need those. And rewrite this as -5/3 x minus 9 is equal to -2/3 x minus 6. What we want to do is group all of our variable terms on one side of the equation, all of our constant terms on the other side of the equation. So we can start off by adding 5/3 x to both sides, and by adding 6 to both sides, which will give us -9 plus 6, or -3, is equal to -2/3 plus 5/3, which will end up being 3/3 times x, or just 1 times x. And we have our solution, -3 is equal to x. So we reduce that system of two equations down to a single equation with one variable, and we solved it using methods we've established before. That gets us half of our solution. Now what we're going to do is take this result that we came up with, -3 is equal to x, and plug that back into either of the original equations. It doesn't matter which one we choose, but I'm going to go ahead and go with equation 1. And I'm going to rewrite it as y equals -5/3. And in place of x, I'm going to plug in -3 minus 9. And then we just solve for y from there. This equation is already solved for y, so all we need to do is evaluate the expression on the right-hand side. -5/3 times -3, our 3's will reduce and leave us with -1. So we'll have -5 times -1, or +5 minus 9, which gives us y is equal to -4. So our solution to this system will be the xy coordinate pair, -3, comma -4. Keep in mind our solution will always be an xy coordinate pair when we're solving these systems of equations.